The next topic to discuss is unitary matrices and real orthogonal matrices. So unitary matrices can be viewed as a generalization of orthogonal matrices. Orthogonal matrices are, are real. That's it. Sentries are real. And unitary matrices, it can be complex also. Fine. Suppose we stack n orthonormal vectors with dimension cross 1. We get a unitary matrix. These vectors are actually these vectors x1, x2, etc., xn, where xi belong to Cn. If you stack all these together, you get your square matrix. And it happens that if you do U Hermitian U, and U into U Hermitian, both will be equal to I. Why? Because of orthogonality. Only for the same i's, for same index, you'll get 1, and for all others, it'll be 0, because they're all mutually orthogonal to each other. And if it's the values are real, then you get Q. Q transpose Q is equal to Q. Some distinction you have. So all these terms are actually equivalent. If U is unitary, one thing you can say is U into U Hermitian is equal to U into U Hermitian U is equal to I. This is similar to A into A inverse is equal to A inverse A is equal to I. So which means that the inverse of a unitary matrix is actually it's Hermitian. You just basically have to take the Hermitian of it. And U into U Hermitian is also, so if U Hermitian U is equal to U, U into U Hermitian U is equal to I, then U into U Hermitian is also equal to I, because we've already seen that if AB is equal to I, then BA is also equal to I. This is something which we have proved earlier. Okay. Then U Hermitian is also unitary. Yeah, because U Hermitian into U Hermitian whole Hermitian is equal to U Hermitian into U, which is again equal to I. Then columns of U form an orthonormal set. This is already, we have seen that we are starting it as an orthonormal set. Rows again form an orthonormal set. Another important property is the L2 norm of Ux is equal to is equal to L2 norm of X. So it is actually it preserves lengths. So if you apply a unitary transformation on X as a linear transform, this is why this is so. Ux is equal U of X. This is very simple. Square is equal to X transpose U transpose Ux. Okay. This is equal to X transpose X equal to X. So all these things are equivalent. What it means is, if somebody tells you that a transformation Ux preserves length, the Euclidean sense, you can say that U is an orthonormal, unitary matrix. Similarly, if you say that the rows of the matrix U are linearly independent, then it means that they form an orthonormal. Then that's a unitary matrix. Columns are beyond linearly independent, orthonormal. Then they are unitary. If a Hermitian of a matrix is unitary, you can say that Hermitian of U is again unitary. All these things are actually same. And if you say a matrix U into B, you can say all these things are actually equal. That's all about the unitary matrices.